Good morning everyone, and welcome to the next instalment in the worked exam answer series. Today I'm having a look at an AQA A-level NMR question where we have got to think about the standard that we use in NMR spectroscopy and why we use that as the standard. We've then got some proton NMR spectrum information, and we're going to be asked to put together the structure of a particular compound P, where we've been given the molecular formula. Then the question goes on to ask us about some different isomers of P, where again they've given us some information about the number of peaks in their proton NMR spectrum, the integration ratio, or the functional group and the type of isomerism that they might have. And we're going to have to draw some structures for those different isomers. So I'll highlight and go through how I'm going to approach all of these questions, and what I would like to spend a bit of time on is explaining what I would annotate on this table of information and on this figure here, where we can see the splitting patterns of the different peaks. So hopefully all of that will be helpful, and I will get started. Okay, so it starts off by telling us that the non-toxic inert substance TMS is used as a standard in recording both hydrogen and carbon-13 NMR spectra. We have to give two other reasons why TMS is used as a standard in recording NMR spectra, and we also then have to give the structural formula of TMS. So TMS stands for tetramethylsilane, which then looks like this with the silicon in the middle and then the 4 CH3s around the edge. So the structural formula would be like this. In terms of the other reasons we use TMS, first of all, because we've got a CH3 coming out of every position from the silicon, all 4 carbons are in the same environment as each other, so that would create one singlet peak on the carbon-13 NMR spectra, and all 12 of the hydrogen atoms, so the 3 on each methyl group, they're also all in the same environment, so again we would get one singlet peak for all of those hydrogens. So that's one reason. And the second reason is that the carbon atoms within this compound are the most shielded compared to lots of other organic compounds, because it's rather unusual for carbon to be more electronegative than another element, but carbon is more electronegative than silicon, which means that the electrons in these carbon-silicon bonds actually sit closer to the carbon nuclei than they do the silicon nuclei. And NMR works by comparing the relative shieldedness or de-shieldedness, not sure they're words, but hopefully you understand what I mean, of the carbon nuclei. So if this is the carbons in their most shielded state, then that means everything else comparatively is going to be found further, what we call upfield, to the left of the spectra, and that will then enable us to see how the environments of different carbon atoms affects their chemical shift. So those are your other two reasons. Next up, we've been given the proton NMR spectrum of compound P. We've got figure 1, where we're going to be able to deduce the splitting patterns, and I'll show you what I'd annotate on there. And then in figure 2, we've been given the chemical shift values and the integration ratios. And you might not get a figure like figure 1, you might get the splitting patterns as part of the table. I think I prefer to have them in the table, so I might also translate that information down here, because we can use the splitting patterns and the integration ratios to help us to see whether certain peaks are due to be next to each other, i.e. the hydrogens would then be next to each other in the compound. And then we've got 3 questions where we have to use this information to basically deduce what's going on in different parts of the molecule. So in the first question, we've got to explain the peak at 2.2. And then if I turn over, we have to then explain the peaks at 3.5 and 1.2, and then the peaks at 3.8 and 2.6, and then use those to put P together. So that's what I'll do now. So the first thing we've been told about compound P is its molecular formula, which is really useful because we're going to need to make sure that we've got the right number of each of these types of atoms, but also it's going to help us when we're thinking about what these different peaks are representing, how many oxygens we're going to have, so how many different oxygen-based functional groups we can have. Now, I've labelled the splitting patterns of the peaks on here, but I've also then added them to the table. So T for triplet, Q for quartet, T for triplet, S for singlet, and then T for triplet, which we can get from the fact that all the triplet peaks are split into 3, the singlet is just 1 peak, and the quartet is split into 4. Then I've also written how many hydrogens they need to be adjacent to in order for these hydrogens to create a triplet. So to create a triplet, the hydrogens would be next to 2 neighbouring hydrogens because we use the n+1 rule. The number of neighbouring hydrogens plus 1 gives me the triplet. So for the quartet, the number of neighbouring hydrogens would be 3. 3 plus 1 is 4. That gives us the quartet. Triplet, again, next to 2. Singlet, next to none, because 0 plus 1 is 1. And then the triplet, again, would need to be next to 2 hydrogens in the neighbouring environment. Now, what I was saying before about noticing peaks that would then be next to each other, if we look at the integration ratio and how many hydrogens need to be in the adjacent environment, this peak here, there's 2 hydrogens in the environment that need to be next to 2 others. This environment has 2 in it and also needs to be next to 2 hydrogens. So those 2 peaks should be next to each other. And then for the pink boxes, we've got 2 hydrogens in this environment, which need to be next to 3. This environment has the 3 in it and needs to be next to 2. So you're looking for sort of the inverse pattern between integration ratio and how many hydrogens are in the adjacent environment flipped around for another peak somewhere in the molecule. Singlets being next to no hydrogens won't be next to any other hydrogens in the environment, so they should never be appearing next to other hydrogens, because otherwise they wouldn't be singlet peaks. So we're then going to use our data sheet, and if we look on the data sheet at chemical shift 2.2, there's only one option for what it can be, which is hydrogens on a carbon adjacent to a C double bond O. We know that there's 3 hydrogens in that environment, so on that neighbouring carbon, I've drawn my 3 hydrogens like that. For the next 2 peaks, we were asked to have a look at the ones at 3.5 and 1.2. So the 3.5 peak had an integration ratio of 2, the 1.2 peak had an integration ratio of 3, hence I've put that number of hydrogens on. Looking on the data sheet, 1.2 is an RCH3, so a CH3 attached to another carbon with some hydrogens on. And at 3.5, we've got hydrogens on a carbon adjacent to a single bonded oxygen. And so they've kind of given you a big hint by asking you to talk about these 2 peaks together, which is exactly what we figured out in the table. So 3.5 and 1.2, they were the ones that I went round in pink. So I'd already seen that they were going to be next to each other before I then came to answer the question. And the final fragment is the 2 purple peaks that are going to be next to each other. So 3.8 and 2.6. 3.8 again is hydrogens on a carbon adjacent to an oxygen, and 2.6 again falls in the region of hydrogens on a carbon adjacent to a C double bond O. Now it causes some confusion when you've got an O single bonded in 2 different fragments and you've got a C double bond O in 2 different fragments. That doesn't mean that we have 2 different C double bond O's, and it doesn't mean that we have 2 separate C single bond O's, not least because we only have 2 oxygen atoms in our molecular formula. We can have hydrogens on carbons either side of the C single bond O, and likewise we can have carbons either side of the C double bond O, which is what we've got. So what I've tried to show here is that the carbonyl that I drew in the peach colour for the first fragment is the same carbonyl group as I've then drawn above, and then the C with the 2 H's next to the O that I've drawn there, that O is then the same O here, so I've done it in pink and red. And then that's how I've put those together. Now I would always be checking for my NMR structures that A, they match the molecular formula, C6, yep, H12, yep, O2, yep, that the splitting patterns work. So peach would be a singlet, the lilac-y purple would be a triplet, the pink would be a triplet, the red would be a quartet, and this fuchsia-y purpley colour would be a triplet. And that matches with what was in the table on the other side of this page. And then we could also check integration ratios, so 3, 2, 2, 2 and 3, which again, going back to the table, we've got 2 with 3 in and 3 with 2 in, and they are in the right combination. Always worth checking, because sometimes there will be very similar structures where one will be wrong for one really tiny little detail and the other one will be correct. So it's always worth checking back against the data. What you might also find helpful, which I sometimes do before I go on and answer the questions, is look on the data sheet and just draw the fragments that appear. So for 1.2, I draw a little arrow coming out my table and I do an R, CH3. And again, I'd put my 3 hydrogens on because the integration ratio is 3. And then again, if you can't figure out any of the peaks connecting together, or it hasn't broken the question down and it just says, right, for 6 marks, what is the structure of this compound? If you've already got all the fragments drawn out around the table, you're then just piecing together the different parts of the puzzle. And I know I make that sound a little bit easier than I know it is, but with practice, you start to pick up on things like, ooh, pink peaks need to be next to each other, the lilac peaks need to be next to each other, and other little things like that. So the more questions you do, the better. If you've got a specific question you want me to have a look at and do a worked answer for, please feel free to send it my way. Okay, I'm going to do some annotations for the next 4 questions, which are all drawing different structures of the molecular formula C6H12O2. So I'll annotate the key information, draw my structures, and come back and explain those. Okay, so on to the final part of this question, part C, where we are going to be drawing some different isomers of P, same molecular formula, 6 carbons, 12 hydrogens and 2 oxygens. So the first thing we've been asked to draw is 2 different esters. Both esters only have 2 peaks in their proton NMR spectra, and both peaks have the integration ratio of 3:1. Now, if we've got 12 hydrogens in total, we can work out how many hydrogens need to be in each environment. The total there is 4, 12 divided by 4 is 3, 1 times 3 is 3, 3 times 3 is 9. So we need 9 hydrogens in one environment and 3 in the other. So the first thing that I always do, if I know what the functional group is I always draw that first. So I drew the C double bond O, C single bond O for both of them. And 9 is a pretty good question to get. You might have initially thought, oh my goodness, how am I going to draw 9 hydrogens, in the same environment? But actually there's only one way to do that, which is to have a carbon to which there is bonded 3 CH3 groups, because then all 9 of those hydrogens will be in the same environment because they're all on a carbon that's bonded to a carbon with 2 other CH3 groups and a single bond O. For the 3 is also a fairly standard number in NMR, representing a CH3 group. So we can have one ester where we have the 9 hydrogens on the right hand side of the structure after the single bond O and the CH3 before the C double bond O. And in the other ester, we can just flip that round and have the 9 hydrogens and the 3 CH3s on the left of the structure in front of the C double bond O, and have the methyl group at the other side, because they would be different because of what is adjacent to this methyl group here. We've got a single bond O there, and there the methyl group is adjacent to a C double bond O. And as we saw in the earlier question for P, they appear at different places on the spectra because they have different chemical shift values because of the influence of the single bond oxygen and the C double bond O on the relative shielded or deshieldedness of the carbon atoms. So those would be your 2 esters. Next up, we've got an optically active carboxylic acid with 5 peaks in its carbon-13 NMR spectrum. So the first thing I recognised is to be optically active, I need a chiral carbon. So that was one of the key things in my mind all times. The other thing, we had 5 peaks, but we only have 5 peaks, but we've got 6 carbons in the molecular formula. So 2 of the carbons were going to have to be in the same environment. So again, I was thinking about how I was going to do that. So again, I started with the carboxylic acid group. That took 1 of my carbons, so I then had 5 more to draw. Then I was kind of thinking about my chiral carbon and thinking, right, well, maybe I should try and make this next carbon chiral, because if I put a hydrogen in a CH3, the C double bond O that side with the OH is again different. And then if I've still then got 3 carbons to draw, then the bond to the left is also going to be different. So I made carbon 2 my chiral carbon, carbon 3 is the 3rd different carbon environment. Then I was like, okay, have 1 carbon next door. And then if I pop 2 CH3s on there, those 2 carbons of the CH3s are in the same environment, and then that would give me my 5 peaks. So that was how I attended to that one. And then finally, and it may be that there's more than one possible structure for this, but the final question said to draw a structure of a cyclic compound that has only 2 peaks in its carbon-13 NMR spectrum and no absorption for C double bond O. So the first thing I then thought was, how am I going to get my oxygens in there if I've not got C double bond O's? So the first thing that I thought about was alcohol groups, because I knew that was going to enable me to keep 12 hydrogens within the cyclical structure. Again, if there's only 2 peaks and we've got 6 carbons, we're going to have some symmetry. Now, we've got the plane of symmetry that runs vertically through the structure, and we've also got the plane of symmetry that goes horizontally through there as well. And that means that the 2 carbons that have the OH groups on would be in one environment, and the other carbons with the CH2s would then be in a different environment, because each of these, in sort of the dark bluey grey colour, is a carbon with 2 hydrogens adjacent to another carbon with 2 hydrogens, and then to the other side is adjacent to a C with a H and an OH. And we can say the same thing for all 4 of those. So this one, C with 2 H's, adjacent to another C with 2 H's, adjacent to a C with a H and an OH. So they're one environment, and the light blue carbons with the OHs are a separate environment because they've got the OH on, which the bluey grey ones don't. The other structure that I have been thinking about since is to make what we call an ether. So we could, again, to keep the symmetry, slot an oxygen in there and in there between the carbons and leave that as just a H and that as just a H. And if we did that and we had the O's in there, we would still then have these 4 bluey grey carbons in the same environment, because again, they'd all be adjacent to the oxygen of the ether group and adjacent to a C that would then have 2 H's on. And then these 2 light blue carbons would still be in a different environment from the other 4, because they would be 1 carbon further away from the O that I would put in there and there. So there's not always only going to be one answer for what you can have. But I guess I felt that thinking about the alcohol groups was perhaps a bit more straightforward and a bit more like what the majority of you might choose to do when you saw that you couldn't have a C double bond O. If you've drawn alternative structures for any of those final few questions and you want me to have a look at them, please do let me know. Leave me a comment, send me a DM, send me an email, however is comfortable for you to get in touch with me. And like I say, if you've got any requests or you've got any other NMR questions you specifically want me to have a go at, let me know. Thanks, guys.